Okay, everybody, welcome back. In this segment, I'm going to talk a little bit more about the right-hand rule. And we mentioned that before. Let me skip back real quick. You probably remember seeing this right here for vectors, right? Multiplying vectors together. So if this is if the red or the green, I get my colors wrong. If the blue A vector is your radius and your B vector is your force, then that results in a torque vector that would be C right there. So you're cross-multiplying these together. Well, we're going to continue to use the right hand to visualize vectors, torque vectors. Instead of having them kind of pointing, we're just going to think of the radius and the torque acting together to cause a turning motion. All right? And so if you think of your hand, and I'm trying to do this, but of course you can't see me doing it, but imagine this right hand right here. You have these fingers kind of curling over towards you. Let's see if I can get a red color right here. They're kind of curling over towards you, kind of like that, all right? That is the direction of rotation. So if I guess you were looking down, I guess on top of your hand, it would be curling in, what would that be, the counterclockwise direction, right? So if you're looking down kind of from this, like if this arrow is pointing right up towards you, you would see these red arrows kind of rotating around in counterclockwise direction. Well, that's actually the direction that the torque is being applied in, but we need a better way to draw that as a singular vector. We can't really draw vectors very well in a circle because if you were to draw the torque like this being represented as like a circle, it's just, first of all, it's not in a constant direction, so we can't really even call that a vector, but we still do need to think of the torque as being a vector to differentiate that direction of motion from, we'll say, this direction of motion right here. They definitely are different vectors. And so the way the convention that we've come up with to describe this torque created by the red direction of motion is by using the right-hand rule. And so we call this, oops, that's not red, that's green. We call the arrow that is coming out, that is represented by your thumb, we call that the direction of the torque vector. All right, because the opposite direction, rotation of the opposite direction, is obviously the opposite torque vector, even though it is rotating around a circle, but that's going to be illustrated as that right there. So somebody who was right-handed, as my understanding is, that I guess a greater percentage of the population is right-handed than left-handed, decided, hey, let's use our right hand to illustrate this and have everybody agree on the direction that the torque vector should be aimed at. So if you curve your four lower fingers around, if that's your direction of motion, then your thumb sticking out is going to be the direction of the torque vector that is going to be represented. All right. A way to think about this is, and if you have a blank, you don't even need to draw this, but I'm going to illustrate this. A way to think about this is in terms of helicopters. All right. So I drew two helicopters here without blades. Now most helicopters have one set of blades on the top, okay? So I'm going to try to draw this sort of, I guess, at an oblique angle, all right? So looking down on top of it, it's not even very balanced, is it? Oh, that's awful. Try that one more time. See if I can center it like so. That's a little better, like that. All right, so looking down on top, that would be the counterclockwise direction, right? And so that would be, we would say that would be a positive torque. So use your fingers. So if you're looking sort of down on top of it, what direction would you be pointing your right hand? Well, your fingers would be kind of curving around this way, which means your thumb on your right hand would be pointing up, right? So that would be the torque that would be applied right there. The torque vector that would represent that torque vector. It doesn't mean that the propeller is necessarily moving that direction, but it just means that that's the direction of the torque. Now remember, when we talk about forces, and torque is a force applied at a radius, forces never occur singular. They always occur in pairs. And so, if you have a motor right here that is creating a force at a radius that's going in this direction, then there has to be some sort of opposite pair that is applied to the rest of the helicopter. And that's true. If all you had was this torque right here, that would mean that the propeller would spin this way, and the rest of the helicopter would be spinning the opposite direction, and everybody in the helicopter would be spinning around like crazy. Well, that's not good, right? You can't have that. You want the bottom of the helicopter to maintain its orientation and yet still balance out this turning force or this torque up here. So what we have is in most helicopters, we have a propeller at the back right here that applies a sideways, all right, or in this case, looking down on top, that would be a clockwise torque to the helicopter so that it balances out. So this torque 2 right here balances out torque 1 so that the forces can exist in pairs, but that the rest of the helicopter doesn't actually go spinning. All right? So the way the helicopter does turn around is that this sideways directed propeller spins faster or slower and applies more or less torque to balance out the torque of the propeller. The main propeller, I should say. All right? Now, some helicopters get away without having a backwards, or I should say a sideways propeller, because they have 2 propellers. I know there's a Russian attack helicopter that is actually kind of cool. It has one propeller spinning like that. So, all right, so that'd be torque 1 directed that way. And there's another propeller right below it that is, let me get this straight, spinning that way. So if you turn your hands, let's see, so that looking down on the top, or we're looking down from overhead, the red one, you would result in your thumb pointing up. But if you had to curve your fingers around, your 4 fingers around in the green direction, that would force you to point your thumb downwards. Like that, so that would be torque 2. Doing the same thing that this sideways propeller does right here. But if you have 2 propellers spinning opposite, ooh, I don't want to do that. Am I going to erase all this? Oh, I am. Darn it. Oh, I didn't mean to do that. Anyway, if you have 2 propellers spinning opposite directions, it does the same thing as a sideways propeller, which creates the balancing torque so the helicopter doesn't spin around and go crazy. All right? So the whole point here is that we can clearly see, all right, this torque up is balancing out that torque downwards. It's because there is one torque applied counterclockwise and another torque applied clockwise. Same thing right here. You achieve the same thing with 2 different propellers. This is achieved with 1 propeller and 1 sideways propeller. So that's why we use the right-hand rule. We use that to illustrate torque in, you might say, one direction. Yes, it is true that torque represents a force that is changing direction constantly, but the convention for illustrating that is having the torque drawn as coming out for this red one right here, or going down for the green one. So that's why we use the right-hand rule. If you spin around, let's say a bicycle wheel, all right, if you spin around a bicycle wheel, the torque is drawn as coming out at right angles from the radius, right? It doesn't mean the wheel is going to fly that way. It just means that's a way of representing the torque that the wheel happens to have, whether it's clockwise or counterclockwise. Okay, so that's why the right-hand rule. Get used to using the right-hand rule to illustrate the torque. So even though this is going around, you might say clockwise from overhead, the torque that would be illustrated would be a singular straight line vector kind of coming upwards from the palm of the person's hand right there. So get used to using the right-hand rule and thinking about using torque or representing torque in terms of your thumb pointing outwards. That's it for this segment. Thanks for following along. I'll see you on the next one.